Good morning. I invite you to think of a world that is optically native, where most information is not only transmitted in the optical domain, but it is manipulated and processed in the optical domain as well. Small-scale photonic integrated circuits have allowed us to make tremendous strides in our ability to transmit data in the optical domain. We use photonic integrated circuits to transmit vast amounts of information across continents using wavelength division multiplexing. We utilize photonic integrated circuits to sense the natural world through things like LiDAR. We use photonic integrated circuits to create new wavelengths that allow us to interact with atoms. But I'd like to think bigger, beyond tens or hundreds of components, but hundreds of thousands of components or millions of components within a single circuit. I'd like to think about very large-scale photonic integrated circuits. And these circuits can be leveraged to allow for sophisticated processing in the optical domain. There are three key areas that would allow for such large circuits. The first is advanced integrated photonics platforms. Platforms that allow for light amplification through the integration of diverse material sets. Platforms that allow for full-scale circuit fabrication. And circuits that allow for diverse wavelength generation and manipulation. And we've made great strides in developing these platforms, and there are now photonic foundries that allow us to create very whole wafer-size circuits. We also need to think about co-designed algorithms and architectures. Photonics is not a drop-in replacement for electronics. It is unique in its own right. And we cannot constantly be trying to stick photonics as a drop-in replacement to electronics. Instead, we need to co-design the system architecture with photonics in mind and bend the architectures and algorithms to the uniqueness of photonics. And finally, we need to think about manipulating and inventing at the circuit level. And we need the tools that capture the physics to allow us to create those complex circuits. Now, why would we want to move towards the photonic domain for more processing? First, I want to point out is that there are unique physical differences between electrons and photons, between fermions and bosons. Photons lend themselves, from the basics of physics, to very fast processing and very efficient processing. It takes very little information, or no energy, to transmit a photon vast distances. Electrons, on the other hand, lend themselves to storing information in memory, and of course, we have electronic transistors. This has led to CMOS electronics in the digital space that we have built most of our infrastructure about. And photonics, as I said, should not be a replacement for electronics. We don't want another CMOS electronics. We want to create unique photonic circuits. So we are not trying to replace digital electronics, and we're not really looking at the general purpose computing. Instead, what we want to do is take advantage of computation by propagation. Just by propagating light through a photonic circuit, we get nearly energy-free and fast computation. If we look at where we are today, we're in the area of simple circuits, simple circuits that are built out of maybe complex components that involve lasers, some modulators, waveguides, And this has allowed us to use photonics to connect continents, to connect data centers, to connect microsystems within that data center. And we're quickly moving into an era where data in motion is in the optical domain. But we should be thinking now about what can we do next. And in order to do that, we need to stop thinking like device physicists. Stop thinking the answer to every new application is a better photodetector, modulator, or laser, and instead think about optical circuit designers, building advanced functionality based upon the circuit design rather than strictly relying on an individual device performance. And doing so will allow us to build up to functional blocks and complex circuits that push us towards that millions of number that I had put forth. And if we redesign our architectures for these circuits, we can move towards photonic-based systems instead of electronic-based systems. Now, the community has already realized that there are some things that photonics is uniquely suited for. It's uniquely suited to transmit data, as I've already mentioned. It's uniquely suited as well to do certain functions, such as matrix multiplication and Fourier transforms. But the architectures that we've thought about putting these circuits into have been drop-in replacements for electronics, which means that there's frequent conversions between electronics and photonics. And that E to O conversion, or O to E conversion, is very expensive in terms of energy and in terms of time, and you're not actually processing any data when doing it. So we need to think about minimizing those conversions, moving more to the optical domain, and composing algorithms and architectures that take advantage of what photonics is uniquely good at. Here, I'm showing an example of an AI accelerator. But as you can see, because we're constantly going to a touch point in electronics, the overall system performance is dominated by the energy and the overhead associated with the electronics. And you don't fully realize the benefits of the optical systems. So we need to think more holistically, not just at a single circuit level, but at the system level in terms of how we would redesign systems to fit in optical circuits. Of course, nothing is without challenges. And one of the big challenges is optics is basically analog. And so as you scale the circuit, dealing with noise degradation and amplification as you scale the circuit becomes a major issue. So we need to think about how we could inherently design these circuits to allow for large cascades of components without being limited by signal-to-noise degradation. And there's, I'm sure, innovative ideas in that space that will allow us to add light in without necessarily adding noise into the system. Additionally, the physics that is important at the single or couple circuit level is not always the same physics that will become important at the many circuit level. There's other second order effects and third order effects become more important as we cascade many devices together. And we need to understand what that physics is, and we need to make sure we have the tools that track that physics through large photonic systems. So here we are, photonics at DARPA. This idea of very large scale photonic integrated circuits didn't come out of nowhere. It's based upon a foundation of investments DARPA has been making into the photonics ecosystem for some time. This ecosystem has included the PIPES program, which allowed for intimate integration between photonic chips and electronic chips, and the maturity of modulators, detectors, and comb sources within the integrated photonics ecosystem. Lumos has allowed for the integration of gain into the photonics ecosystem, creating new wavelengths in integrated photonics, and large-scale complex circuits capable of fan-out. And then the HAPPY program is looking at advanced packaging of photonic chips, allowing for chip-to-chip interconnections, as well as dense three-dimensional routing around a single photonics chip. And as these programs have advanced the capabilities of integrated photonics, the ecosystem as a whole has also advanced, allowing for foundry access, and really allowing us to now think about not just the devices, not just how we're going to make the circuits, but how we're going to design the circuits and how those circuits fit into the next level of the system architecture. And that's why today we're poised to build upon this foundation and create highly scalable complexity with very large-scale photonic integrated circuits, opening up new applications in the photonics domain. With that, I would love to hear ideas of where you think photonics can fit into systems, how we can re-architect systems in the photonics domain, and innovations you have that would help advance the overall photonics ecosystem. Thank you.